Today I would like to talk about certain conventions to do with how we write down search models. So normally, when you write down a value function, you write it down so that the value is measured from the beginning of the period, if we're talking discrete time. So by that I mean the agent has woken up at the beginning of period t, and they're about to consume whatever it is that they get in that period. And then there may be some uncertainty revealed later on in the period, at which point the agent knows what to expect tomorrow, and then the period ends. In period t plus 1 begins again with consumption or utility or whatever it is that generates value for the agent. The conventional value function is measured from the perspective of the beginning of the period. However, there's an alternative possibility, which is to measure values at the end of the period. So the uncertainty is being revealed, the agent is about to go to bed, and the next thing they look forward to is consumption at the beginning of the following period. Now the difference is that that consumption is going to be discounted because we're still at the end of the previous period. Now this doesn't affect behavior, but it is going to affect the form of the value function, and it's going to be particularly useful because what it means is that you end up with a value function that looks exactly the same as the one you would get if you're writing down the problem in continuous time. Let's begin with discrete time, and let's say that v tilde is the conventional value function, whereas v is going to be the alternative value function. Alternative, again, in terms of timing. So let's say the environment is one where the agents have a payment x each period, and with probability alpha, they switch to payment y. What's the conventional value function going to look like? Well, it's going to be a function of x, and again, we're waking up in the morning, we get our little payment x, and then with probability alpha, one thing happens, which is that we switch to having payments y instead. Now, normally, when we write down the agent's future value, we need to discount it, and typically we discount it with some discount factor beta, which is less than 1. However, in this context, it's useful to instead express beta in the following way, as a function of a discount rate, written like so. Of course, for any beta, there's a corresponding r greater than 0. For any r greater than 0, there's a corresponding beta, so this is just a change of variables. With probability alpha, the agent is going to wake up with y tomorrow. With probability 1 minus alpha, the agent stays with x. And that's it. Next, let's write the alternative value function. And again, it's not going to have the same values, and in this particular model, everything is simple. There's no behavior. The agent is passive. V of x, again, remember, is defined at the end of the day. So everything tomorrow is discounted. The agent is going to wake up in the morning and get x. Then with probability alpha, they're going to move ahead with y. With probability 1 minus alpha, they're going to stay with x. And notice I don't need to write the discount factor here because it's already inside. Multiply both sides by 1 plus r. Like so, and like so. Of course, this cancels because it equals 1. Now let's unpack this product and this product here. And now let's realize that the term Vx is on both sides. So let's subtract v of x from both sides. Finally, let's collect terms with alpha, and we end up with this. This is what's called the value function in flow form. What it's saying is RV, which is, in a sense, the flow of what you get from holding the asset Vx, gives you the following payments in each period. 1, it pays you the payment X, and 2, with probability alpha, the following event can happen. You lose, going forward, the value of your asset X, but you gain, going forward, the value of your asset Y. So, as mentioned earlier, expressing the value function in this way gives you a financial interpretation of what it is that's happening to this agent. They have an asset of value Vx, which has a flow payment and some probability of that asset being switched for a different one. As you have more practice with such models, you'll find it convenient to just write things down this way from scratch, from the beginning. Because, again, all you need to keep in mind is what payments is the agent getting right now, and what are the possible events that could change their situation going forward. Next, let's look at the continuous time problem. Here, there are going to be some slight changes. V is going to be the value function. The agent gets a flow payment of X, and with some Poisson rate alpha, they may switch from X to Y. And the key thing is that the PDF of this occurring over some interval of length t is the following. It's alpha e to the minus alpha t. This PDF is going to be important for us. Next, suppose we keep x up to some moment in time, big T. What does this agent get? To write this down, we're going to need, first of all, to integrate from 0 to big T. Then, remember, this agent discounts. In continuous time, how do we discount? We discount exponentially with some rate r. The agent gets x at every instant, so we integrate over this. And then at the end, in moment big T, the agent switches to v of y. So we write v of y and discount it appropriately. So the value is not this. This is the value of switching from x to y at date big T. And so to figure out the value of this situation, this state X, or this asset X, if you will, which gives you a flow X, we would need to integrate over all the possible big T dates with the appropriate probability distribution function. So we have to take this integrate it over all possible big T's, so that's from 0 to infinity, d of big T, and then, as mentioned, we need to multiply this thing by the PDF of the date T. Excellent. Next, let's expand this, which has two terms. So let's bring this inside there. And that way we'll be able to deal with this integral here, and then this one here, followed by this one here. Okay, this one can be simplified because we can just add these exponents here. And what are we going to get? This is going to be fairly straightforward because when you integrate an exponential function, all you're going to end up with is another exponential. Just have to be careful with the exponents. Let's take out any multiplicative terms because, of course, they're not going to affect the form of the integral. And here we have an alpha we can take out, and we also have v of y that we can take out. Now it's easier to see what it is that we want to integrate. This thing is just going to be the definite integral from 0 to infinity of this over the exponent. And here we're going to have the definite integral from 0 to big T of this expression over its exponent. Now we have to evaluate these. Notice that because there's this minus sign here, this is the same as just switching and getting rid of the minus sign. And notice that this evaluated at infinity is 0, and this evaluated at 0 is just 1. So that's easy. Here you can do the same thing. Multiply by -1. That's equivalent to switching these things. So this evaluated at 0 is just 1 over r. This evaluated at big T is just this expression. And so we've cleared the first of our integrals. Next step, this is done on the right. On the left we have another integral, and we can deal with it by observing that this can be brought inside. So if I do that, we're going to get this expression, and we can simplify this once again by adding the exponents. Finally, once again, we have these integrals which are exponential. So we're going to end up with the definite integral evaluated between 0 and infinity of this over its exponent, and this over its exponent. There. We can get rid of these minus signs here by switching the limits of integration. And finally, observing that either of these with infinity plugged in is going to equal 0, and either of these evaluated with big T equals 0 is just going to be 1 over the denominator. So we're ending up with something that looks increasingly simple. Finally, let's combine these fractions. This one needs to be multiplied by alpha, and this one needs to be multiplied by alpha plus r. Then we can combine them, and we'll see that we're simply going to remove alpha. We can also quickly see that r is going to cancel here. Notice also we have an alpha outside, which is going to cancel with the alpha in the denominator. And slowly but surely, we're left with a simpler and simpler expression. We can multiply both sides by alpha plus r. Of course, this equals 1, and this equals 1. Subtract alpha times Vx from both sides. And lo and behold, we end up with exactly the same expression that we had when we solved this problem in discrete time with the alternative timing convention. Once again, notice this is much more simple than going through all the derivations. You could just write down this expression as discussed by simply saying that r times v is the flow that you get from holding the state x, r of vx that is. It's the payment x, or any payment that you get while holding the asset, plus the probability alpha of anything changing, and then you write the value of the new asset that you're going to have, and you subtract the value of the asset that you would be giving up. And note that, of course, a typical search model is going to be more complicated. For example, suppose y is uncertain and is drawn from some PDF f, and suppose also you don't have to take y if you prefer x. How do we change things? This is of course going to be a more typical search environment, because the whole point of search is that you are looking for things and you get to choose them if they're better for you. Well, first of all, we would have to integrate this over the possible values of y with their weights from the PDF. And then if you're allowed to choose whether you want to switch from y to x, all you need to do is say that you're going to get the max of this or 0. So then this now, instead of being the flow value of getting some payment x, which might randomly switch to y, instead now we have the flow value of getting a payment x with the option of switching to y with probability alpha. And it's an option because, again, you can do it if it's in the money, you can do it if you prefer y to x, but you don't have to. You can always just choose to stay with what you have.